Welcome again. Today we start our next lecture on algorithms design and analysis course, sorting algorithms, a quick sort. A quick sort, like merge sort, is a divide and conquer algorithm. It splits the array into smaller arrays until it ends up with an empty array or one that has only one element before recursively sorting the larger array. However, it's an anyplace sort, meaning that we do not need extra copies of the arrays or space. It does, however, require stack memory for all recursive calls it makes. A quick sort is an unstable sorting algorithm. You remember, a stable sorting algorithm is one in which elements with the same value appear in the same relative order in the sorted array as they do before the array is sorted. It may happen sometimes in quicksort, but the quicksort does not guarantee that. A quicksort is a highly efficient sorting algorithm and is based on partitioning of array of data into smaller arrays. A larger array is partitioned into two arrays, one of which holds values smaller than the specified value, usually named pivot, based on which the partition is made, and another array holds values greater than the pivot value. A quicksort is also called partition exchange sort. As I mentioned, this algorithm divides the list into three main parts: pivot, the central element, elements less than the pivot, and elements greater than the pivot element. Pivot element can be any element from the array. It can be the first element, the last, or any random element. For example, given the following array, if we choose the pivot, the last element 24, then after the first partitioning, the pivot will be here in its right position or sorted position. All the elements on the left are less than the pivot, as you see, and all the elements on the right of the pivot are greater than the pivot. So the pivot is in its right position. Usually, we need two functions to implement the quicksort. The quicksort main function, we pass to this function the array, the index of the first element, and the index of the last element in high. And we perform the loop while low less than the high. We call the partition function, passing it to it the array or sub-array with the low and high indices. After returning, I will show you later, after returning from this function, in PI, we will have the index of the pivot. Here, the pivot. So we recursively call the left part, but now we pass the sub-array with these indices, low, and instead of the high index, we place pivot index -1. And we recursively call the function quicksort with the right subarray, but now the indices are changed to low. We pass pivot index +1, and high is the same. So after executing the partition function, the pivot will be here on its proper position, and we retain I plus 1, the index of the pivot. The partition function can be implemented in several ways. We have to organize two indices. They can grow in the same direction, or the two indices can grow on the opposite directions. Another implementation. We first assign low -1 to index, assign the last element to the pivot, and we start a loop from for j in range low high. Remember, if array sub j less than the pivot, then we increment I and exchange. This is a swap between the elements ai and aj, and we loop again. If the array sub j is not less than the pivot, we do not perform here anything. We loop again. After finishing the loop, we exchange here, or we swap the pivot with the array I plus 1. So we place the pivot on its proper place. Here, an example. This is the array. So you see low 0, high 9, and we choose 7 as the pivot. Here is the partition function. You can trace how it works. First, we assign I to -1, low -1, it's -1. Here, statement 2, I -1. Here we have the array elements, as you see, with their indices. Pivot array I, pivot 7, and we start a loop for j in range low high. So statement 4 here, j0. Now we compare array sub 0 with pivot. Since 3 is less than pivot, then in statement 6 we increment I, now I0, and we exchange a sub I with a sub j. Here no change, since 3 will stay on its place. We swap 3 with a 3, nothing. Next j, here j1. So we now compare a sub 1, 9, with the pivot, which is 7. Since 9 is not less than 7, the condition is false. We do nothing here. We do not perform statement 6 and 7. And we go back to 4, and again we increment j. Now j is 2. Array sub 2 is 5. 5 is less than 7, so we increment I becomes 1, statement 6, and we swap array sub 1 with array sub 2. These are I and j. So we swap 9 and 5. On statement 4, next j becomes 3. Now array sub 3 is 14. 14 is not less than 7, so again we increment j. Now we compare 15 with 7, 15 with pivot. The condition is false, so we increment j. Now 8 is not less than 7, we again increment j, 6. We compare Now 6 is less than 7. The condition is true. So we increment I here. I becomes 2. And we swap array sub 2 with array sub 6, which is 6 and 9. We swap them, as you see. They are swapped here. Again, we increment J. Now J is 7. And we compare array sub 2 since I is 2. We compare array sub 7 with the pivot. Array sub 7 is 2. Since 2 is less than 7, so we increment I and swap 2 and 14. We swap array sub 3 and array sub 7 here. Again, we increment here J 8 and we compare 4 with 7. Since 4 is less than pivot 7, we increment I and we swap array sub 4 with array sub 8. Here 4 and 15. Again, we increment J. Since J is 9, we exit the loop and go to statement 8. In statement 8, we swap the pivot with array sub I plus 1. Array sub I plus 1 is array 5. So 7 here. And we retain the index of the pivot. Now the pivot is in index 5. We retain I plus 1, which is the index of the pivot, to the calling function. Do you see here all the elements on the left are less than the pivot and on the right greater than the pivot? Regarding time complexity, on the worst case, the complexity of the quicksort big O is in square. But if the pivot is selected in a good way, so it will divide the array into 2 almost equal subarrays on each iteration, then you know the partition will take only log n and n passes, so the complexity on the best case and on the average case will be n log n. The quicksort is not stable sorting technique, so it might change the occurrence of 2 similar elements in the list while sorting. But it is in place, meaning we do not need extra space except for the stack memory for the recursion calls. Here is a comparison between quicksort and merge sort. Both algorithms are divide and conquer. Merge sort, as you remember, is not in place, but quicksort is in place sorting algorithm. So space complexity big O in merge sort is n. Here, if we do not consider the stack memory, the big O for space complexity is 1. If we consider the memory required for stack recursion calls, big O will be log n. The complexity for merge sort is big O n log n. For a quicksort, in the worst case, big O is n square, while in the best case or average case, It's n log n. There are many different versions of Quicksort that pick pivot in different ways. We can pick the pivot as the first element or the last element as we implement in our example, or we can take any random element as a pivot or pick pivot as a median element. Here is the Python program for the Quicksort. Here is our array. We pass to the Quicksort function the array with the index of the first element and the index of the last element. On the main function, while low less than high, we every time partition. But do you see on partition, we have to change the indices for the subarrays. For the left part, the index will be low, pivot -1, and for the right part, the low will be pivot index +1 to high. I trace with you how the partition function works through example. Thank you.